All right, so I've got this simple RC circuit example problem here that we have all come to know and love. This is just the standard charging RC circuit. I'm going to say let's assume that V out at time t equals 0, right, just before t equals 0 is 0, basically assuming this voltage is 0, so the capacitor is initially discharged, no initial conditions in the circuit, and we've got this step input that pulses from 0 to 5 volts. I should write that this is volts at time t equals 0. And we basically want to determine V out of t. We're going to do this using everything we've learned so far. And so let's start by writing a KVL loop around the circuit. I'm also going to note that this V out of t is equal to Vc of t, right? That's the voltage across my capacitor. And I should certainly draw a loop current that I call I of t. Okay. And of course, that's equal to IC of t, that's equal to IR of t. This is just a series circuit, right? So if I were going to write a KVL expression, actually, last thing, let's note that our input can be modeled as a unit step function multiplied by 5. So we'll just say it's 5 times u of t, right? Because, of course, our unit step goes from 0 to 1 at time t equals 0, and my source is going from 0 to 5 at time t equals 0. So we need to multiply that by 5 to model our input. Okay, so let's do a quick KVL. It's going to be Vn of t, which is 5 times u of t, minus I of t times r, minus Vc of t, which is 0. Okay, well, we have two variables here, so we either need to represent Vc of t in terms of I of t, or we need to represent I of t in terms of Vc of t. And because we want to determine basically the output voltage, Vc of t, V out of t, it makes sense that we want to replace this I of t with something in terms of Vc of t. Okay, so let's go back and grab, this is from several slides ago when we were doing our other example, our expression for the voltage across the capacitor in terms of the current. So where are we? Let me make sure that I get, okay, so we're here. So this is our expression here. And so if you remember, well, first of all, we're saying that there's no initial condition, so we can just assume that this term goes to 0. And we're basically saying that this is equal to Vc of t, right? And so if we put this into the S domain, well, right now, let's just convert this over to the S domain really quickly. That's pretty trivial at this point. So this is going to be 5 over S, right? 5 times 1 over S, minus I of S times R, minus Vc of S is equal to 0. And so we basically want to get I of S in terms of Vc of S. And so if we remember, we converted this Vc of t, we can, if we use time integration property of Laplace transforms, we can say that this Vc of S is equal to 1 over C times 1 over S times I of S, right? So we can say that Vc of S is equal to I of S over S times C, or we can say I of S is equal to Vc of S times SC, okay? So now we go back into our expression over here, and we can substitute this for I of S. We're going to get 5 over S minus Vc of S multiplied by S times R times C, minus Vc of S equals 0. We want to isolate Vc of S, and so we'll go 5 over S is equal to Vc of S multiplied by 1 plus SRC. So what did I do there? I basically took these two terms, moved them to the other side, factored out of Vc of S. And so now the last thing I need to do is divide both sides by 1 plus SRC, and I get Vc of S is equal to 5 over S times 1 plus SRC. I'm getting there, right? We're getting to a point where we could potentially, because our goal is to find V out of t. Right now we're in the S domain. Should probably note that we took the Laplace transform of each of these terms, right? So this was our transition from the time domain into the S domain. All right. And so here we are, and we're getting close to being able to wrap this up. But right now, we need to do one more thing. We need to isolate the s in this term so that we can do partial fraction expansion on this this function of s, this VC of s that we have here. So let's factor out an RC. So I can say that this is equal to 5 over s times RC over s plus basically 1 over RC. And now I could move that RC term to the top. So my numerator is 5 over RC, which is a constant, divided by s times s plus 1 over RC. And now I could do partial fraction expansion on this function. So I could rewrite this VC of s is equal to a over s plus b over s plus 1 over RC. And of course, that's equal to this function here. And we need both of them in order to complete the partial fraction expansion. All right, so I'm going to leave this problem here for now. This is an aside. This is how we determined I of s in terms of VC. So I'm going to draw an arrow here. Right, that's how we plugged in. Actually, it'd probably be better to do this. All right, so I'm going to leave this problem right here. We're basically at a point where we can perform partial fraction expansion on VC of s. Our final goal is to find V out of t, which is equal to VC of t. So once we can get this partial fraction expansion completed, we would be able to Laplace inverse these two terms and find our function VC of t pretty easily. So that's what we're going to do in the next video. I'll leave this video here, and we'll see you guys in the next one.